continue the afternoon session. Our first speaker is Noa Keshet from Technion, and she will talk about element abundance measurements and absorption measure distribution for the stellar black hole GRO J1655-40. So Noa, the floor is up to you.
Thank you very much. So yes, my name is Noa Keshet. I'm a PhD student at the Technion, and thank you for the opportunity to allow me to present, even if it is remotely. Today I'm going to present to you the work I have been doing with my advisor, Professor Bechar, about measurement of abundances in the X-ray binary GRO J1655-40's outflow. So just some motivation for X-ray binaries outflows. Measurements of different physical attributes in the outflows in the X-ray could be the key to, for example, density of the wind, as was shown by Miller et al. From 2008, specifically for GRO. In the same paper, he also calculated the distance from the radiation source. And there has also been some debate about the launching mechanism, specifically for this X-ray binary, starting with Miller et al. From 2006, who suggested magnetic driving, continuing to Fukumura et al. From 2021, as opposed to a thermal driving mechanism that was shown by Tomorrow, Dunn, and Mao from 2023. But so far, elemental abundances has been somewhat forgotten, at least for these types of sources. And this is very interesting since it can tell us a lot about the past of the system, and we can infer the progenitor that exploded in the supernova that left the black hole that we see today. That is the motivation for our work. So just a quick introduction to GRO. It is a low mass X-ray binary consisting of a stellar mass black hole of about 6.6 solar masses and an F-star companion of about 2.7 solar masses. And it's a relatively small system with a separation of 10 to the 12 centimeters. But the most interesting part about it, maybe spectroscopically thinking, is its outburst from 2005, which we were able to observe with Chandra. Here I am showing the spectrum from the Keigo grading, and as you can see, it is a very unique spectrum. It has really great signal-to-noise ratio and many lines. It is very rich in line, which is probably why it has been the subject of many works for almost 20 years now. So what drew our curiosity in this spectrum is the fact that we see some pretty rare elements that we do not usually observe lines of in the X-ray, specifically odd Z elements. Here I'm showing small segments from the spectrum of these lines. And so we were curious to ask, what are the abundances of these elements, and in general, what are the abundances in the entire outflow? So at first we approach this with a pretty simple method. We see the Lyman alpha lines of 17 different elements, and we can measure the optical depth. And so if we have the expression for the optical depth tau equals sigma the cross section times the ionic column density. And we know sigma is of course theoretical, and it's about the same for all Lyman alpha lines, meaning straightly from measuring tau I can get the ionic column density, and from there I can get to a measurement of the abundances by the further relation. But this method fails here, and the reason is saturation. And here I'm just showing an example of saturation. This is a small segment from the spectrum, and I want you to focus on the two strongest lines of hydrogen-like neon, the Lyman alpha line and the Lyman beta line. When I measure their equivalent width, they're almost the same. The relation is almost 1 between them, even though theoretically I expect the relation to be the oscillator strength relation, which is much smaller, meaning I expect the Lyman beta line to be weaker. So I'm dealing here with saturation, and in order to bypass this problem, we turn directly to the curve growth. We calculate the theoretical equivalent width as a function of the ionic column density. Therefore, we get the curve growth. Specifically here, just an example of the silicon Lyman alpha line. Of course, the Lyman alpha line is actually a doublet, but we do not resolve this in the spectrum. Therefore, we can only measure the sum, and so that is what we compare to. And I can use this to translate my measured equivalent width directly to ionic column density. So just a few things to note here in this figure is, first of all, you do see I'm starting to get saturated in the line. I'm turning into the flatter part of the curve. So we are dealing with saturation, but more than that, we need to consider that this largely affects our uncertainties. This is a relatively well-measured lines in our spectrum. And indeed, the uncertainties on the equivalent width are relatively small. It is constrained well. But since we are on this flatter part of the curve, when we translate to ionic column density, we get larger uncertainties. And of course, this will be reflected in our final measurements of abundances. Finally, I cannot go to abundances just yet, because I need to remember that the abundance is proportional to tau divided by the hydrogen column density. So I need to ask myself, what is the behavior of the hydrogen column density in this outflow? And first of all, of course, I cannot measure directly hydrogen in X-ray. So necessarily, whatever measurements I perform, it must be relative to one of the ions. That cannot be avoided. But we think that not only NH is a function of Xi, but it's also a complicated function of Xi. And the reason for that is I want you to notice these pairs, these dashed orange lines, are pairs of hydrogen-like and helium-like ions of the same element. Of course, if I measure abundance of an element, I expect to get the same abundance from whichever ion I calculated. Therefore, we see this behavior of a very steep slope to indicate that as I go towards lower Xi values, I have less column density. And we use these pairs of different ions that we can measure in our spectrum in order to tailor the entire distribution of the column density as a function of Xi and get an entire behavior for the column density. And we will have to correct for that in order to get the abundances. And this is a very significant correction. And you can see the point of oxygen here, which is our furthest end that we see in our spectrum, the lowest Xi forming ion we have. And indeed, this correction will be significant for the oxygen since the trend predicts that there is much less column density when we go towards such low Xi values. So if I'll summarize the method, I measure each line locally with the Voigt function. Then I calculate the equivalent width directly from the fit. I translate this measured equivalent width to ionic column density using the theoretical plot. Then I correct for the column density based on its Xi, and I approximate here that each ion is formed at the peak Xi value. And then, as I already mentioned, this is a relative measurement, so all the corrected ion are taken relative to one of the elements. And finally, I normalize everything compared to the solar values. So our results. First, just a consistency check. Wherever possible, we measure not only the alpha line, but also the beta line and the helium-like line. And generally, there is an agreement. But there are places where there are slight discrepancies between the beta line and the alpha line. And this could be due to the width of the line, the turbulent velocity we assumed. And I will touch more on this later on. But more interestingly, we see an anomalous high oddsy elements, a trend of the oddsy elements that are being supersolar. And this is very interesting since, like I mentioned, this could tell us a lot about the past of the system. And specifically, we compare our measurements to yields of supernova model simulations from Nomoto et al. From 2006. And we see we need a high mass progenitor of 40 solar masses. But more interestingly, I want you to follow the green line, which shows peaks exactly at the oddsy elements, which is the case when we have a supersolar progenitor that explodes in a supernova due to neutronization processes. And this is the first time something like this is measured, which makes it so interesting. Another thing we can compare is measurements taken from the companion by Hernandez, Robelo, and Israel from 2008. They did work in the optical band. They measured the atmospheric abundances of the companion in the system. And it is very clear that there are very large discrepancies between what we measure and what is measured on the companion, which brings out the question of what is exactly the picture in this system? What is the physical picture? And is the alpha we're seeing the same as the material on the atmosphere? Is it the same as the material that flows from the companion to the black hole through the accretion? And this is still a puzzle. It is not something we yet know how to explain. So there are a few remaining questions which I wanted to touch. First of all, like I mentioned, the width of the lines. We took the same width for all of the lines as a constant based on several lines that we were able to resolve, specifically using the third order of the grading. But we are now testing to see if perhaps keeping the velocity as a free parameter and feeding not only one or two lines, but an entire series of lines for the same ion could improve our results. Since of course we are expecting to get a coherent picture and to reach a value that fits as many lines as we have, and this is indeed a very rich spectrum, so we want to take the full advantage of it. Another thing we are now testing is if the approximation of the fact that the ions are forming at the peak, perhaps it is not a good enough approximation, perhaps we need a better one, or perhaps we need to make a more detailed calculation of the ion forming at the entire Xi range. And as I mentioned, there is still the puzzle of the origin of the wind. What is the full picture of the system? How can we see such large discrepancies and such a different picture when looking at the companion and from looking at the outflow? Maybe this tells us something about where the outflow exactly is located, how far away it is. We do not yet know. We will be happy to hear thoughts. And finally, this also leads me to the age of the system. We don't see a supernova remnant, but we think this perhaps are the remains of the same material that exploded in the supernova. So maybe this tells us that this is not a very young supernova, but relatively young, because we still see the material. And as I mentioned, it fits models of a very massive progenitor, and a pretty small black hole was left behind. So there is a lot of the material roaming around the system, and is it what we're seeing? Is it not? These are all questions we are still facing. So just to conclude, we performed independent measurements that are not model related of 17 different elements. Some of them are rare that we do not usually see in the X-ray, and specifically the Oddsy element, which also points us towards models of type 2 supernova from a high mass, high metallicity progenitor. Thank you.
So time for questions. If not, then I can start with a question. And it's interesting to see fit that the example that you showed of this absorption line, it looked like there's a weak emission line superimposed on that. Does that influence your estimate of the equivalent widths? Yeah, like in the example that you showed there.
Yes, it can affect. I will say, yes, I will say that we do not see many emission lines across the spectrum, that we're not sure that there is emission that has to be considered. But even more than that, I can say that each line I measure locally, so I try to capture the continuum as well as I can, so the equivalent width measurement will be as accurate as possible. And also there are blue shifted lines, so I'm expecting if we would have seen emission lines at rest, that we will be seeing more of a Signy profile or something like asymmetrical profile that we don't see for at least most of the lines.
Okay, thank you. Time for another question on one on Zoom. Yeah. Okay, Alfredo Luminari, thanks for the talk. I wonder how critical is the assumption that all the ions form at the peak ionization value, and in case, how this can be circumvented?
Sorry, I didn't hear the last part.
How you can circumvent the assumption that all the ions are formed at the peak.
We're right in the midst of what? Sorry, I'm sorry, my connection is a bit. Sorry, can you hear me?
Yes, yeah.
Yes, so as I mentioned, this is exactly one of the points that we're now testing to see if this is an over-exaggerated approximation that we did. So it's a great question, and we are right now trying to think how we can test and show that it is not so, that it still works, or correct our results if we find it is an important approximation. Thank you.
Okay, thank you. You had a question, short one?
Just to remark on what you said, the main points for which you have emission line on top of the absorption is for the iron complex at like 7 keV, and you can actually add an emission line and try to see how much it affects the equivalent width of the absorption line, and you basically have 20-25% of uncertainty on the equivalent width, which is not going to affect significantly your results afterwards. That's all.
Okay, thank you.
So it's time for our next speaker, Peter Kosec, who will give a review talk about accretion disk winds in X-ray binaries.
Hi. First of all, I would like to thank the SOC for inviting me to give this very biased review of high resolution X-ray spectroscopy of X-ray binaries, focusing on my work, which is accretion disk winds and outflows. And we've already heard a great summary of other science in high resolution X-ray spectroscopy by Maria earlier today. So accretion, of course, is the phenomenon of infall of a material onto objects such as black holes and neutron stars, but it has been very early realized that it's a very highly energetic process which can also result in ejection of material in form of outflows. Here on the right, I'm showing an example of, I'm showing two figures from the seminal paper of Shakur and Sunev from 1973, which show that for a supercritically accreting system, the radiation pressure is going to be important, and it will produce powerful outflows from these collapsars, or I guess what black holes were called back in the day. And theoretically, there has been a plethora of identified possible launching mechanisms for these winds that includes radiation pressure, magnetic forces, or thermal driving. And in fact, such outflows have been discovered in X-ray binaries already before the era of high-resolution X-ray spectroscopy. Here I'm showing some of the earliest examples from ASCA from late 90s, where these absorption dips have been discovered around 7 keV in ASCA spectra. But these outflows were later confirmed, of course, with Chandra X-ray, the spectrum of which is shown on the right from, I think, GX13+1, a neutron star X-ray binary, and also from XMMRGS. So now immediately you can see the huge improvement in spectral resolution and the data quality over the previous ASCA spectra. And nowadays, we know of multiple dozens of examples of disk winds in X-ray binaries. They have been detected in all sorts of X-ray binaries that include black hole X-ray binaries, an example shown on the top right, which is the same source that we've just heard about in the previous talk. They were also found, outflows were also found in low magnetic field neutron star X-ray binaries. An example is GX13+1 on the bottom right. And more recently, also we detected them in a high magnetic field X-ray pulsar, Hercules X1, an example of this spectrum is shown on the bottom left. These winds usually show high column densities reaching 10 to 23, as high as 10 to 24 per centimeter squared. They also show high ionization states of log xi of 3, 4, or 5. Therefore, we usually observe only hydrogen and helium lines from these winds because they're almost completely ionized. And they also typically show low velocities of about hundreds or maybe a few thousand kilometers per second, although there is a star here because some exceptions apply, and I'll talk about these towards the end of my talk. And such winds or similar winds and outflows were also found in AGN, as we've heard yesterday, but also in tidal disruption events that have not been mentioned here in this conference before, but are also great sources to study with high resolution X-ray spectroscopy. And of course, also in white dwarfs that we heard about this morning. But a good question to begin with is, why do we care at all about these phenomena? Are they just a curiosity, or do they actually matter physically in these systems? And the answer is that they are potentially very important because they have the potential to carry away a significant fraction of the original infalling mass. Therefore, they can significantly modify the inner accretion flows or accretion flows of X-ray binaries. And also by non-conservative mass transfer, they can modify the evolution of X-ray binaries. And also in some systems that I'll talk towards the end of my talk, these winds can reach relativistic velocities of dozens of percents of the speed of the light. And then therefore, they carry huge kinetic powers, which if these powers are efficiently deposited in the neighborhood of X-ray binaries, they can affect them significantly. How do we study these outflows? Basically, when an outflow is a disk wind is launched from the disk, it is illuminated by the hard X-ray or X-ray radiation from the X-ray source, which might be an X-ray corona or the disk itself. And so this plasma is ionized, and if it crosses our line of sight towards the X-ray source, it will absorb some of the source radiation, creating an absorption line spectrum. These absorption line spectra are particularly powerful because they're relatively simple to interpret with photoionization models. And they inform us about the physical conditions of the material in this point where it is crossing our line of sight towards the X-ray source. However, that's also the big disadvantage of these spectra is that we're only probing the properties of the material in this one point. And therefore, we can imagine that this is only a very limited picture of this full 3D structure and geometry of the outflow. And it is then very difficult to constrain its total mass outflow rate, total energetics, and therefore the total impact on the system. Conversely, the material out of our line of sight will re-emit some of the source radiation into our line of sight, creating an emission line spectrum. This then encodes this full 3D structure, but because it does so, it is also much harder to interpret because we have to model this full 3D structure. Additionally, specifically in X-ray binaries, these emission lines are very weak. This indicates something about the geometry of these outflows, and they can also be confused by other emission line mechanisms, such as reflection, that is known to occur in these sources. So here on the bottom right, I'm just showing an example, again from GRO J1655, where you can see that the absorption lines are very deep, very prominent in the spectrum, and the emission lines, if present at all, are much weaker. Nevertheless, by studying a population of X-ray binaries with absorption spectra, we can make some important interpretations. There was this very important population study by Gabriele Ponti from 2012, which looked at a sample of black hole X-ray binaries. And they noticed that specifically outflow detections only occur in high inclination low mass X-ray binaries. This says something about the geometry of this outflow, which is likely not spherical, but instead the structure is equatorial, focused towards the disk with an opening angle maybe as small as 15 degrees. They also noticed that these winds are primarily detected in these black hole X-ray binaries in soft states, which are dominated by strong thermal disk emission, and not in the hard states. Although, of course, we've heard earlier this morning the opposite example from AMXPs. But so it's still an open question, what is the condition of this wind? Why do we not see it so strongly or at all in hard states? And the possible interpretations are that this wind could be over-ionized by the hard SED from the hard states, which is dominated by the X-ray corona. And these features might then be much weaker or undetectable in these systems. Alternatively, the conditions of the wind that we observe in soft states might be thermally unstable in the hard states, again, making this wind impossible to detect at such ionizations. Or finally, maybe the wind is just not present in these objects in hard states at all. But recently, there has been this quite surprising discovery also of outflows in X-ray binaries, but not in the X-ray band. There have been detections of outflows with similar velocities of about 1,000 kilometers per second in X-ray binaries, but seen through optical, near-infrared, and UV band lines. Here on the right, I'm showing an example from the helium-1 line in the optical band in Swift J1858. And what you can see is like a P Cygni profile with a strong blue shifted absorption with a velocity of about up to 1,000 kilometers per second, and a strong emission red wing. And this feature has been detected in multiple epochs and seems to be strongly variable with time. So this looks like a typical outflow, but the most surprising thing here was that this was detected in the hard state. So this suggests that outflows in X-ray binaries are much more complicated than originally thought. And most recently, there has been a paper from Munoz Darias and Gabriele Ponti from 2022, which in fact detected both an X-ray wind and an optically detected wind at the same time in one object, P404 Cygni. In the top part of this figure, I'm showing the silicon 14 line, which is seen in X-rays and shows a P Cygni profile with strong blue absorption with a velocity of about 1,000 kilometers per second maximum. And on the bottom is again the helium-1 transition, which shows the same shape, same kinematic shape of both the absorption and emission. This maybe indicates that this outflow might be the same part of the same complex multi-phase flow, which is originating somewhere in the disk and is outflowing from the X-ray binary. But of course, much more work has to be done to establish this connection more securely. A good question, of course, is what mechanisms power these winds? The initial idea is radiation pressure, but since these are standard sub-Eddington sources for at least the most of X-ray binaries, this cannot be radiation pressure on electrons. Instead, this could be radiation pressure on the many UV transitions, which can boost the radiation force. But these transitions cannot be over-ionized, because then you lose this force multiplier. So this interpretation is not actually good for X-ray binaries, the spectra of which peak directly in X-rays, and where we expect that all of these UV transitions are fully ionized. A promising mechanism is magnetic driving. Under certain magnetic field configurations, a wind can be launched along these magnetic field lines, as shown in the paper by Keigo Fukumura from a couple of years ago, creating an outflow of matter, which is following these magnetic field lines. However, this magnetic force depends heavily on the field configuration and strength, which is nearly impossible to study at this stage. So these outflows are very difficult to study or to prove that we are looking at a magnetic wind. But I imagine Keigo will talk a bit more about this in his talk following me. And finally, another promising method of accelerating these outflows is thermal driving, which is also called Compton heating, in which case an outflow is simply formed by irradiation of the outer part of the accretion disk by hard X-ray radiation and basically evaporating it by giving it such a thermal boost that it starts evaporating, creating an outflow. So necessarily, this mechanism only produces very low velocity outflows with velocities of about 1,000 kilometers per second, or maybe even lower. And it requires big accretion disks because you can only evaporate the very outer part of this disk. Now, in the next part of my talk, I'll be talking about a project that I've been involved in and leading for the past couple of years on a very specific and unique system called Hercules X1. And I will try to convince you that this system gives us a unique insight into specifically the vertical structure of the wind, overcoming this problem between absorption line spectra and emission line spectra very neatly. Hercules X1 is famous for having this 35-day period of alternating high and low states. Basically, for each 35 days, you get 2 high states and 2 low states. And it has been studied, this cycle has been studied for the past 50 years, basically. And the interpretation is that the disk of this X-ray binary is seen almost edge-on and is warped and is precessing every 35 days. And as you can see in the simulation, the disk is tilted, twisted, and is precessing. And at most times of this 35-day cycle, some part of this disk is obscuring our line of sight towards the inner accretion flow, which produces most of the X-rays. And then we see a low state. At other times, we can see directly at the neutron star, which is in the center, and then we see a high state. But what's very neat about this is that during different parts of these high states, our line of sight towards the neutron star is probing different regions above the disk, specifically at different heights above the disk. And it's going through this highly ionized disk wind that we observe in the system. So in the schematic on the bottom left here, what I did is I fixed the warp disk so it is not precessing, and instead I'm moving the observer between these high and low states. At different parts of this high state, then our line of sight is passing through different part of the streamline of the outflow and at different heights above the disk. Therefore, by doing this observation throughout this high state, we can sample the vertical distribution of the outflow properties. And so to use this unique opportunity to understand the vertical distribution of the wind, we requested and carried out a large campaign with XMM, Newton, and Chandra to observe exactly this. And the results are shown on the right. Basically, at low precession phases, this is right after the warp disk has uncovered our line of sight towards the neutron star. So we're sampling low heights above the disk. We see high column densities of the outflow, reaching 10 to 23 or more per centimeter square. But as we're progressively sampling this outflow at greater precession phases, that means at greater heights above the disk, the column density significantly drops by 3 orders of magnitude, down to just a few times 10 to 20 per centimeter square. This means that the wind is just getting weaker and weaker as it's expanding higher and higher above the disk. This is in full agreement with the population studies that I've shown before, where we do not see any winds in low inclination sources, as well as in agreement with the hydrodynamical simulations of disk winds. We also see a strong evolution of the ionization parameter, where we see that the wind is getting less and less ionized as it rises higher and higher. But the neat thing is that not only we can track the position of the wind, we can also predict how exactly the warp disk is precessing at each point in time. Therefore, if we can estimate how far is the disk wind from the ionizing source, we can also estimate where our line of sight should intersect the streamline. And doing this calculation for all of the observations that we have, we can create a 2D map of this disk wind. Here in the x-axis is the horizontal outflow position, on the y-axis is the vertical position. And the color scale is on the left is the column density of the wind, and on the right is the ionization parameter. So what we see is an outflow that originates close to where we predict that thermal disk wind should originate. Then it rises from the disk at an angle that we can calculate to be about 12 degrees away from the disk. And as it rises and propagates into space, it's getting both weaker and colder, and we can also determine it's getting much more clumpy. So this is a very unique example of where we can study the vertical structure of a disk wind, and these measurements can be directly compared with simulations of disk winds in X-ray binaries, hopefully to determine the wind loss mechanism and its total energetics and mass outflow rate. Now, in the last part of my talk, I would like to talk about a different kind of X-ray binaries, with the ultra-luminous X-ray sources, which are known to be the most extreme X-ray binaries and have not been mentioned much here in this conference yet, which is actually a bit of a shame because they greatly benefit from high-resolution X-ray spectroscopy. It has been decades ago when people realized that there are X-ray binaries observable in external galaxies. And then in the 80s, with Einstein Observatory, it was found that some of these X-ray binaries are much brighter than the ones that we see in our galaxy. Here is an example from the Gartwheel galaxy, which is, I think, a merger, and it shows vigorous star formation. And when we look with Chandra CCD in the X-rays, we see many very bright X-ray sources, and some of which exceed the luminosity of 10 to 39 ergs per second, which is the Eddington luminosity of a standard stellar mass black hole. So, and it's been a long discussion. Much research has been done to in order to interpret what these objects really are. They could be powered by simply more massive black holes, intermediate mass black holes accreting at super Eddington rates, or alternatively, they could be powered by super Eddington accretion onto standard mass X-ray binaries. They are also often found in star-forming regions in galaxies, maybe suggesting in association with high mass X-ray binaries. And also, many times they're located in massive bubbles of ionized gas, hundreds of parsecs large. And I'm showing an example on the left, which is a bubble around the famous ULX called Hallmark 9X1. And the existence of these bubbles suggests that the luminosity of these sources is not very highly beamed. And in fact, the very high luminosity is real. Nowadays, we know that the majority of this population is indeed powered by super Eddington accretion onto X-ray binaries. And the final and the most important piece of evidence for this was that pulsations were detected from a few of these sources, maybe now up to 6 or 7 is what we are. And therefore, these pulsations suggest the presence of a neutron star as the accretor powering this source, and which means that this object has to be super Eddington accretor. Super Eddington accretion is naturally associated with radiation pressure. And in some of these sources, we're talking about 10 times or 100 times Eddington, as far as 500 or 1,000 times the Eddington fraction. So as the material is accreting towards the central source, which could be a black hole or a neutron star, the radiation pressure gradually becomes more and more important, and it begins puffing up the accretion disk into a geometrically thick disk, and begins launching these powerful outflows of ionized matter. And since the radiation pressure is probably the strongest in the inner accretion flow, these winds are going to be naturally very fast. They're going to carry huge kinetic powers. And on the bottom right, I'm showing just an example from one of these simulations of super Eddington accretion from Takeuchi et al., which shows just how very strongly puffed up is the inner disk, and how this outflow is powerful and is very messy and it's very clumpy. And people have looked for these outflows, first starting with CCD resolution spectra. But all they've detected were just these broad residuals, which are very hard to interpret. What was really needed was to use high resolution gratings to resolve them into individual lines. But this is, of course, a great challenge because we're talking about extragalactic X-ray binaries. So despite their luminosity, their fluxes are very low. And even the highest quality X-ray spectra that we have of them are just few thousands of counts often. But nevertheless, in a few cherry-picked ULXs with the highest quality data sets that have hundreds of kiloseconds of exposure, it was possible to resolve these spectra into individual lines. And Pinto et al. In a paper from 2016 actually identified some of these lines and specifically noticed these highly blue shifted absorption lines from neon, iron, and oxygen, which correspond to outflows with velocities of about 0.2 speed of the light, and therefore indicate the presence of a very powerful wind in these sources, as expected for super Eddington accretors. They also detected these emission lines from the same elements, which appear to be rest frame or low velocity gas. And then we also searched for evidence of these fast winds specifically in neutron star ULXs. And because the existence of these outflows in neutron star X-ray binaries has strong consequences on the interpretation of their accretion flows. But these spectra are usually very low quality, and any features in them are not going to be easily to detect just by eye. So we developed a suite of automated spectral search tools to study these spectra in a systematic manner. And in this example, specifically in NGC 300 ULX1, which is a neutron star powered ULX, we generated a large number of photoionization grids over a large number of possible photoionization parameters and outflow velocities, and then fitted all of these different models to the spectra that we had, and detected significant evidence for an outflow with a velocity of about 0.2 speed of the light in this neutron star ULX. And then in the next year, Van den Eyden and al. Also found evidence for an outflow again at 0.2 speed of the light in actually the first galactic neutron star ULX called Swift GO243. So this evidence is important because it limits the magnetic field of the neutron star that is powering this source. Basically, if an outflow is being launched from the inner disk with a very high velocity, that means the inner disk has to exist close to the neutron star, which is limiting the maximum size of the magnetosphere of the neutron star, and in turn, putting an upper limit on the surface field of this neutron star, and therefore indicating that these objects cannot be powered by accreting magnetars, as was originally thought for neutron star ULXs. Now, finally, in the previous slides, I showed a few cherry-picked examples for ULXs with best quality data, but we were also wondering, what about the whole population of ULXs? Do they show these plasma features? Do they show winds or not? And so we performed a systematic study for 17 ULXs with the best quality or with usable quality high resolution soft X-ray spectra from RGS onboard XMM Newton. And what we did was a blind search where we searched for any emission or absorption lines in these spectra. And what we found, the results are shown here in this histogram, where the x-axis is the wavelength and the emission lines are in green and absorption lines are in red. We find that the emission lines are strongly peaked at the rest frame wavelengths of the known ions, like magnesium, neon, iron, oxygen, and nitrogen. So these suggest the presence of low velocity, but still quite highly ionized plasma in these systems. But instead, the absorption line seemed to avoid these rest frame wavelengths of these known ions, and instead concentrate in between them. Therefore, these absorption lines are consistent with originating from highly blue shifted ions, indicating the presence of high velocity outflows, which therefore seem common in the population of ULXs. And in fact, these powerful outflows with velocities of 0.1 to 0.2 speed of the light carry enough energy to inflate these massive bubbles of ionized material, in which many ULXs are located. So just to very quickly summarize, these quints appear ubiquitous in some stages of life of X-ray binaries, but they are very complex phenomena, and we still have much to learn about them. Specifically in ULXs, it appears that powerful relativistic outflows are a common feature among the population, as is expected for super Eddington accretors. And unfortunately, I didn't have time for this, but GRISM has great potential to revolutionize completely this field of outflows in any kinds of X-ray binaries. And just one last sentence for a recent review of high resolution X-ray binaries, high resolution studies of X-ray binaries with also a focus on these quints. Please see Nielsen and Degener from earlier this year.
Thank you very much, Peter. Questions? Yeah, Ms. Ach.
Thank you for a great talk. I was wondering, is there evidence or expectation of transition between different modes of the winds, like thermal versus magnetic, as there is change in the state? So you talked about the inclination angle, but that was all within the thermal wind regime, right? So is it possible that that the modes, I mean, at some times one of them is more efficient than the other one?
I would say that at this point it's difficult to identify, even if we're in one mode or in the other.
Perhaps inclination angle, because if it's magnetic, perhaps low inclination is, I would thought, is more maybe magnetic. But you said also
that's right, but these low inclination winds are not common at all.
So would that mean that magnetic is not the right explanation?
maybe for the winds that we observe, but it could simply be that at low inclinations, the wind is there. It's just not high enough column density to see.
Thank you.
Yeah, behind you.
Thank you for a really, really fantastic talk. So you hinted that now you're seeing those like other wavelength winds. So can you speculate on what is the connection between the X-ray and the other wavebands?
Yeah, so the suggestion, same as Munoz Darias and Gabriela Ponti, I think, is the suggestion is that it's a multi-phase outflow, and that simply in some states it's easier to see the X-ray counterpart.
So how far would the, say, the optical on the or the IR would be away from the disk versus the, do you imagine them to be much more far out, or do they just kind of, I don't know, locally?
They are certainly much colder.
Right.
But as far as I understand, it is very difficult to put any constraints on their position, specifically for the optical winds. For the X-ray winds, we know they're relatively close.
Okay, thank you. There's still two questions online. The first by Alfredo Luminari. Just a couple of curiosity regarding the NH Xi trends versus the precession phase in Hercules X1. First question, is the wind in photoionization equilibrium? And secondly, are the column density and the ionization parameter degenerate?
So to answer the second question first, I think we can separate the NH and the Xi dependence. So I would not say they're degenerate. And the first one, that's a really good question. And I think I think it is mostly in photoionization equilibrium, but we'll see when we do a pulse result study whether this really holds.
Okay, and then the question for Ehud Behar. What is the radial dependence of the ionization parameter they get in Hercules X1? And Keigo can comment if it agrees with MHD winds. So the radial dependence of ionization parameter.
I think it's too soon to say whether this is really the case. I think with Grissom we'll be able to probe this much more precisely, and then it's going to be the time to answer this.
Okay, so other questions, please find Peter here during the break or ask through Slack. So thank you, Peter, again. So the next speaker is Maxime Parra from Grenoble, who will talk about current state of disk wind observations through X-ray absorption lines in the Aran band.
Indeed. All right, so hi everyone, my name is Maxime Parra. I'm a second-year PhD student in co-supervision between France and Italy. And today I'm happy for two reasons. First, because I have the opportunity to present my talk here. So thanks a lot to the SOC and the LOC also for giving me a lot of goodies for an astronomy festival I'm doing in August. And I'm also very happy because it's the first time I'm giving this talk. I've given it a lot of times with the paper out on archive. So please, if you like the talk, you can go check it finally. It's been a while, but it's finally out. So we had a very nice introduction talk, even though Peter said it's very biased. I thought it was very nice. And so I can actually skip almost all of my introduction, so I have more time. So low mass X-ray binaries, lower Schwab overflow, accretion disk, outburst, states. I actually have exactly the same figure on the first absorption line detection. It's quite funny. And 10 years after, we have a lot more detections, and we finally have a first, let's say, global information about what's the physical mechanism and what's the information we can get about the object with the Pony and all in 2012. As Peter said, the two most important informations is that they only detected or almost exclusively detected wind signatures in soft state for high incline or equatorial, if you want, objects. And the third information, as he said also, is that the mass outflow rate of the wind that you can estimate through back of the envelope computations is extremely high. And even though you're not exactly sure of the value of it, you know that it's comparable, if not higher, to the accretion rate, which means that the final, let's say, part of the matter that arrives, to the central object is only a small part of the matter that was coming out from the outside. So of course, if you want to consider the whole accretion ejection process and the whole outburst mechanism, if you're not understanding the winds correctly, you're completely lost. And as of now, I would argue that we still don't understand them correctly, if at all. So it's been 10 years, even like 11 now. And of course, the picture has only grown more complex, even though we still don't have yet wisdom, but it's going to be even worse after that. So we have a lot more exotic detections. We have now detections in the hot state. We have detections in low inclined sources. We have detections at very high blue shift. How do they fit with the first picture? It's hard to say. We still do not know if thermal or MHD are the processes driving the wind. The main issue is that with the current high resolution X-ray spectroscopy instruments, we are not able at all to distinguish between the two because we are not able to resolve the tail that we expect for MHD driving. And finally, in the last few years, we've had the rise of detections in other wavelengths, being AR, UV, visible. And this is also something we have to check if it fits into a global coherent picture with maybe a single outflow, maybe multi-phase outflow, but it's hard to understand as of now because it's only been a few years. My job is not to answer all of these questions. My job is not to give you a part of the answer on a very small piece of the puzzle, which is the X-ray part. So what we did in the last year and a half was basically making an update on the global view of the X-ray winds, at least in the environment, which is the easiest one to look at and the most high SNR part, let's say, for the blue shifts and other parameters of the line is very important. So we take all of the black hole mass X-ray binary candidates from the most up-to-date catalogs. We have 81 sources. We take all of the available, let's say, decent resolution or high resolution high energy spectra. We have Chandra HETG and XMM as a start. This means 240 spectra. You only take the spectra which are good enough in terms of quality to detect lines, of course, because you actually want to look at something for which you can make an analysis out of it. And after a bit of data reduction and a bit of continuum fitting, you can actually start trying to detect your lines first with a blind search. I'm not going to explain to you what's a blind search because we've had it a bit already in the last few talks. And after that, you can try to add Gaussians. I'm sorry for the physical modelists here, but just Gaussians with physically motivated parameters. And the goal is just to estimate the parameters of each individual line, and then their significance individually. If you do not see lines, it's also very important to try to estimate the significance, if you want, of not having line to a decent upper limit computation, because it's going to allow you to constrain your winds afterwards for your physical parameters or for your driving mechanism if you expect to see something which you do not see, right? Without further ado, this is the updated plots for the HIDs that you've seen from the panel 10 years ago. We have a lot more sources. On the panel of the left, you have high inclination and deeper sources. On the one on the right, you have either low inclination or sources with no information. And you can see very easily that there's a few things that are striking, at least for me after watching this for 6 months. On the left, you can see that you only have detections for sources high inclined because, well, the right panel doesn't have anything. And you also have kind of a double dichotomy in terms of position in the HIG, right? So you do not detect absorption lines for hard states. Actually, I'm lying saying that because, of course, GRS 1915, as usual, has some issues with its behavior. But basically, if you take out non-standard states, you only have detections in soft states, and you have only one detections below a certain threshold in luminosity. This is the moment at which I add a huge caveat to my diagram, which is that we do not have the mass and distance estimates perfectly, if at all, for a lot of these sources. So in some cases, you have hidden uncertainties for the luminosity values depending on the mass potential of your black hole, which can be very high or very low. This is the case for this point for GRO J1655-40, which is, as of now, with our fiducial estimate of 8 solar masses, very low in luminosity. But if it's actually just a 2 solar masses black hole, or even a neutron star that has been misinterpreted as a black hole, it could be very much higher in the diagram. So it's still very possible that we have a dichotomy in luminosity. However, if we want to go a bit deeper, we do not, or we cannot, I would say, only look at detections and non-detections. We need to look at the upper limits to know if our non-detections are significant enough so that we can draw a conclusion. And so if we do that, we can come again to our hypothesis one by one. The first being no detections and no inclination. You can see that our hexagons represent upper limits. There are a lot of small, which means very constraining hexagons, even in the high luminosity soft part of our low inclination sample, which means that this is very good for us. We are almost sure we do not see, and we won't see, let's say, detections for low inclined sources. Of course, Keigo is going to say I'm wrong, or show at least 1 or 2 sources that are very different in one talk, but we are focusing on maybe more standard objects at the moment and the standard behavior. For the hardness ratio, my cut here is completely arbitrary, but I'm still able to tell you that you can do the same kind of dichotomy for hard and soft state, and you have a lot of hard states with very concerning upper limits. One of the caveats of that is detection with reflection, but I'm going to talk to you about this a bit later. And finally, the last point for which it's actually being an issue is luminosity, because actually our low luminosity detections are, of course, lower SNR, so it's harder to be sure that we do not have a line, and I would argue that we actually cannot make a definite conclusion about that. Maybe there are lines here that are just low enough in terms of equivalent width that we do not see them. So we can say without, for example, maybe Grism. We can also look at a bunch of different line parameters to try to explain what's going on and try to link the behaviors of the different objects. I don't have time, so I'm just going to focus on the most important one, which is arguably the blue shift. I don't think I need to tell you that Chandra is much more precise than XMM in terms of energy resolution. And I would also say that actually you cannot do anything with XMM in terms of interpreting the blue shifts of the line. As Maria told me a year and a half ago when I started trying to understand the blue shifts of these lines, the Chandra blue shifts are very much centered about zero. The XMM blue shifts are looking very much alike the residuals of the calibration, which is not good for us, of course. So if you take out the XMM blue shifts and just keep the Shannon ones, you have this distribution that you can split between the objects. But basically, if you take off these 3 points, which are points for which you have contamination from lower ionization lines, I'm not going to talk to you about that, you still have a distribution which is not exactly centered about zero with significance. It's significantly not zero. It's a very low blue shift. It's about -200 blue shift, but kilometers per second, but it's there. So there is a systematic outflow for the whole sample. Of course, the whole sample in this case is only 4 objects, with we have a lot of observations for these objects. There is a lot of spread in the data, of course, but we still have a significant mean, so it's interesting for us. I'm going to come back to my HID diagram to tell you something else, which is that, okay, in some cases, we do not see the outflow, right? We do not see the lines. But what about the part of the HID for which we expect to see them? Do we always see them? I think you can say that the answer is no. And now the second question is, why no? Is this no significant? Does this mean that you actually have portion of the HID for which you have the conditions to see the line, but you do not see them in some cases because your outflow itself has evolved? This is the best way to know if your outflow is evolving. If you have, let's say, conditions for you to see the lines, and then you see the lines in one observation and you do not see it with a very different equivalent width or lack of equivalent width in another observation, this means that your outflow has changed. If your HID position, ionization parameter, or your stability curve is almost the same, your outflow must be the one to change. And so you can see here that there are very constraining upper limits for almost all of the sources for which you have lines that are basically each and every one of them interesting points for which to apply MHD driving or thermal driving to try to compare the evolution of the physical parameters you get from applying these models in the cases for which you see lines and in the cases for which you do not see lines. You can try to do the same thing with other sources with no detections, because there are still a few with the right physical parameters for which you could expect to see something here. But the issue is that there are too many, I would say, discrepancies in the inclination parameters. There are too many discrepancies in the possible mass or distance measurements. And so even the points here, despite the fact that they are constraining, are physically not constraining enough. I don't think we can use them correctly. I'm going to start concluding very early because I want to try to give you a bit of an overview of the whole, let's say, multi-wavelengths and literature view of the things, not just what I'm saying. So what I'm saying is that we have 5 sources of detections. All of them are deeper, high inclined. Almost all the detections are soft state, except for non-standard states. And the blue shifts are there, but very low. If you look at the rest of the literature in X-ray, especially in the last few years, well, you still have the vast majority of sources with detections are high inclined, except for 1 or 2, I would say. But the hard state to soft state dichotomy is completely gone. You have a lot of detections in the hard state, but the thing is that exclusively, except 2 maybe, almost all of them are embedded in strong reflection components. And this becomes very tricky business because it's extremely hard to distinguish a residual from within your reflection component for simply a poor fit or an overfit of your reflection component. And I would argue that the issue that we have with the geometry that we apply for the reflection as of now makes it even worse. So until last year, I would argue that almost all of the works that were looking at that were not done properly because their goal was not to estimate the disk wind themselves. It was just, they are basically fitting a reflection model. They find an absorption feature. They're like, oh yeah, let's put a Gaussian. And then that's it. They don't estimate the Monte Carlo significance of it properly. But now there is a postdoc in France doing that, also working with Keigo. He's going to talk to you about that later. This is looking much more promising. And I would have put this in red before. Now I put it in yellow because I still take it with a grain of salt, but I think we're going to have a conclusion, be it, yes, these reflection absorption features exist or no, they don't exist, they're not significant enough very soon, but we're going to have an answer finally. These detections are also different in another way, which is that they are often very, very high velocities. And this is also in discrepancy with the vast majority of detections that have very low blue shifts. You have, of course, secondary components when you fit photoionization models that are higher velocities, sometimes a few thousands of kilometers per second, but they are one, very secondary, so maybe you're overfitting, and two, sometimes it's possible that you're fitting something else because you do not have a good enough precision in the atomic data that you're able to exactly fit your secondary component, which is maybe like 1/10 of the size of the first one. But with my, let's say, basic analysis, I am not able to resolve these components, so this is normal for me not to see them. We will see with physical modeling and better resolved instruments maybe in a year or two if these secondary components are real. Finally, if you add the literature in multi-wavelength, things become even more complicated, but at the same time, they are not so different. You always, or almost always, still have high inclination sources with detections. You do see things in the hard state and in infrared, but that's normal because your constraint on the state for which you expect to see the wind only comes from the stability of your plasma. And for the ionization parameter of your infrared and visible detections, you are not constrained by the same physics. So this just means that the outflow is there no matter when the outburst. That's a very important conclusion. This means that if we don't see it in X-rays, it has to be because something is preventing us from seeing it, not because it's not there. You also have a discrepancy in the blue shift, but I don't have too much time to talk about that. I'm just going to finish by saying that we have a bias in the inclination measurements because, as we've seen in a lot of different talks, the inclination measurement that we have usually parse different parts of either the orbit, the disk itself, its outer parts, its inner parts. So it's very hard to know, as someone who wants to say, oh yeah, high inclinations are linked with winds, which inclination measurements from which part of the disk, I'm almost done, is the one that should be taken into account. So we are continuing the work. We are now analyzing the thousands of spectra in NICER archive and doing modeling at the same time. I'm going to thank for your attention and just say that we have now a visualization tool online, which has every result of the paper and more. If you want to look at things a bit more in detail, please go see it. Thanks for your attention.
Thank you very much for your talk.
Yeah, no, it's okay.
Maybe one short question. Yeah.
Oh, thank you. Nice talk, and good that you show this plot now, because all the sources where you have detection, they cluster nicely in this hardness luminosity diagram,
yes,
except the red source that seems to be spread out.
Do you know which one?
Why is
GRS 1915?
So what
That's
does it
part
mean?
of the answer. Like GRS 1915 doesn't behave that you would expect for other sources. GRS has 22 variability classes now. The issue is that this is not just a soft to hard state transition. There are a lot more transition inside of this in terms of variability and in terms of HR ratio. GRS 1915, you should just plot its, let's say, 3 to 10 keV hardness ratio, is also generally harder than the other sources. So this adds a bias in this case. And on top of that, this point here, for example, is during the change to the obscured state that we had in 2018. And from there, the source is obscured. You have an estimate of the SCD, but the real SCD is obscured, so you have no idea what's the actual value of it. You have huge absorption lines, but this is far, far from standard. This is something that's close to, for example, B44 Cygni during a superdict and accreting rate. And this is not something that we should compare directly to the normal soft to hard dichotomy, because it's definitely not the same state of the disk.
Okay, thank you very much. We have to move on. So thank you again.
Thanks.
So the last speaker of this session is Keigo Fukumura. Yeah, who's able to grab the microphone. Great. We'll talk about equatorial ultra-fast outflows. The floor is up to you.
Okay, thank you. Okay, so good. Oh, yes. Okay, my name is Keigo Fukumura from James Madison University. First, I want to thank the organizer for giving the opportunity and for everyone to staying till the end. I'm going to share a little bit about our recent work about the non-equatorial fast outflows in black hole transient sources, which may be accompanied by really, really high density accretion disks. And these are my wonderful collaborators. And most of the heavy lifting work has been done by Sudeep and Ajay. And before the lunch break, we had a great review talk by Maria about the general phenomenology of Lomas X-ray binaries. And in this session, we also heard about interesting disk winds and other properties of the ionized gas, particularly in the context of black hole X-ray binaries, from Peter and Maxime. And so this time, the sorry. My focus is again on the non-canonical black hole X-ray binary disk winds. What do I mean by non-canonical? Again, these does not seem to be equatorial high inclination winds. And when you look at the property of the accretion disks, they seem to have a very high density. So we're going to utilize both refraction spectroscopy on one hand and also the absorption spectroscopy, which is not necessarily mutually inclusive. So we have two sort of separate independent diagnostics to say something about the disk and also this ultra-fast outflows. And maybe this tells us something about at least some populations of accretion disk winds in black hole X-ray binary transient sources. And I have to apologize because I only have one slide for high-res X-ray spectroscopy, and it's not even observation, it's a simulation, but I will show that to you nonetheless later on. Okay, so this is kind of a canonical, conventional high inclination equatorial disk winds that we have already known. The previous speakers have talked about this already. For example, GRS 1915 on the left, and then on the right, we have GRO J1655 when the system is very bright from accretion disk thermal radiation. You can clearly see ion K, hydrogen-like, helium-like absorbers. In these two objects, we also see a low ionization soft X-ray absorbers as well. The typical properties of these disk winds have relatively moderate column density, maybe on the order of 10 to the 21, or maybe at most 22 atoms per square centimeters. Velocity is also moderate, few hundred kilometers per second, at the most 1,000 kilometers per second. Okay, but do we see any other winds? So MaxCJ 1348 underwent an outburst back in 2019. This is Swift and Maxi light curves. With the onset of this outburst, the X-ray goes up to a few crabs, and then the brightness declines as time goes by, as the spectral state and the hardness ratio changes. On the right-hand side, we see the Q diagram showing the X-ray brightness as a function of the hardness ratio. The NICER and NuSTAR has seen this source simultaneously over 5 different epochs, as you can see. So these are the domain in the Q diagram where we typically expect disk winds. So we looked at the archival data of these 5 epochs, and as expected, the X-ray spectrum, so this is NuSTAR spectra, are predominantly thermal radiation from accretion disk with a very little weak Comptonized power component, except for E1 epoch, which is the beginning of high soft state. So we fit the continuum, and then we noticed that there's a very strong refraction Compton hump with the soft excess residuals as expected from the refraction components. And at the same time, down to about 7 keV, we see a very robust trough due to most likely ionized absorber. The simple photoionization model tells us that the quantum density is huge, 10 to the 22 or more, close to 23 atoms per square centimeters. And ionization of the gas is also very high. The blue shift of this trough tells us that it's near relativistic. So this is more like equivalent to AGN ultra-fast outflows. It's less than 10%, but it's pretty fast for black hole transient sources. And so from both spectroscopic diagnostics, we can learn something about the inclination and also the disk density. So I want to make a quick note about the disk density. So if we just think about, assume that the disk at the inner edge is optically thick, the Compton thick, then just by simple argument, we know that the disk density there should be on the order of 10 to the 18, or maybe a little bit more for 10 solar mass stellar mass black hole. And it's inversely proportional to the mass, so the AGN, it goes down. So when I say high density disk, I'm referring to this 10 to the 18 per cubic centimeter in the context of black hole X-ray binaries, not the AGN. Okay, so we went ahead. This is a very busy plot, lots of information. So I want you to skip over to the third option that we took. We came across with a number of issues related to physical interpretation of the refraction signatures, such as iron abundances and some artificial residuals at the 50 keV, where there isn't really nothing. Also, the disk density is pegged. It's reached the upper value of 10 to the 19 per cubic centimeters. So we decided to go with the different refraction, the high density diffraction model, originally developed by Tomczyk et al. 2018. And so this model utilizes the non-thermal Comptonization continuum with a variable high energy cutoff and abundances. What's more interesting and important for us is that the disk density can go up to 10 to the order of 10 to the 22, which is really high. I have to admit that we don't know much about the atomic physics at this high density regime, but we need some density, high density model. So we thought this is a good start. And also all of these refraction spectroscopy tells us that the inclination of the system is relatively small, not the equatorial high inclination. So when we try to model this 7.1 keV absorber, it's not really easy and obvious if thermal driven can do the job, given that this is a very high velocity, almost relativistic, and the very massive column density, most likely in a very close proximity to the black hole itself. So we adopted the magnetic driving scenario where the global magnetic field lines are threaded on the accretion disk over a large spatial extent of the disk surface. And of course, these field lines are twisted with the accretion disk rotation. And so the ionized gas is lifted up by J cross B force with a huge toroidal motion, but it will be effectively converted to the toroidal motion in the end. And so the magnetic field can easily lift the materials up to a very high latitude, which corresponds to low inclination wind in a paraboloid structure, as you can see here. Thank you. Okay, so just to summarize the essence of this model, we solved MHD equations under steady state axisymmetric assumptions with self-similar prescription in radial direction. So all the physical properties of this magnetic driven wind, for example, density can be written like this, where F is the angular distribution. And this is the most important property, NW. So that's the density normalization of this wind, which is the density of the wind at the innermost launching radius. So this density normalization is a good proxy to reflect how dense the accretion disk is. So we solved the MHD equations to determine the global properties of the magnetic wind. And then we use X star to do post-process photoionization to calculate the column densities that allows us to calculate the library of synthetic spectra. So with these two, we fit the MaxJ 1340 with the absorption spectroscopy in red and refraction spectroscopy in blue. with the focus on density and inclination. They don't match exactly, of course, but they're in a good agreement. Again, given that these two diagnostics are totally independent of each other. So as you can see, it's a very high density and low inclination. So that's our claim from this one analysis. And then we went ahead to look for 3 more transients. This is EXO 1846. You can clearly see the robust absorption features at the large blue shift. We also saw a very strong refraction. So in the end, we get the low inclination, high disk density. Another maxi source, relatively low inclination, high density disk. And then this is the last source, Swift, again, low inclination, high density throughout multi-epoch observations. So this is a punchline. Y-axis is the disk density suggested from the wind normalization versus disk density from refraction spectroscopy. So this group is the canonical standard accretion disk. And some of the sources, they went through an outburst. It turns out that the disk fails to launch winds. And so we only have upper limit for disk density and wind density. But this group is the one that I just talked to you about. It's clearly different and distinct. So we think that this is a real feature and correlation. Okay, and so this is the only high-res simulation. The Chandra 60 kilosecond exposure might be able to tell us something about the substructure of this broad ion K band. So the black one is the new star at the CCD resolution, but with the Chandra, the microcalorimeter resolution, we can actually separate and resolve ion 26 and 25 separately. We actually submitted the TO proposal and asked the DDT, and we didn't get the time. That's life, no hard feelings. But it would be nice to see, what this substructure looks like. Okay, so the take home, I hope I have shown you some, evidence that the high density disks exist, and that those disks, they are capable of launching the low inclination wind, and almost by necessity, those winds have to be very massive, large column density, and they seem to be correlated, accompanied by each other. So this is the regular case, and this is what we are arguing in our work. And so if you know some sources that might have this kind of behavior, then we'd like to know more about the other sources. So please let me know. Thank you so much for your patience.
Thank you, Keigo. Question. Yeah.
You pay me a beer later to have saved your life. Very interesting results. I have a question on inclination, because in your fit, you leave the inclination free in different epoch fits. So do you think this is an effect of the wind precessing at different epochs, or is an effect of a different ionization structure that unveils a different region of the wind in different epochs, or something else?
Yeah, so we haven't really looked into that, but I don't think we are seeing warping effect or anything. So my first response is that we're looking at the similar spatial area throughout the different epochs. But we just want to demonstrate that the low inclination is not just by accident from one epoch. And so we're happy that we are consistently getting this low inclination. Yes.
Was one last question there? I think the ladies want you. Mesa, last short question.
Thank you. So within this high density disk wind, do you expect to have multiple ionization components, or is it?
Right. Yeah, so that's a very good point. at least at the CCD resolution from NuSTAR, we don't see any obvious soft X-ray absorbers, low ionization species, just ion K-band, which is why we wanted to see this source with the Chandra. But I think, yes, there might be some weak features, but it depends on the density distribution of this wind. And so just want to quickly remind you of this, this property here. So that density slope, this P, it must be very steep so that we only have ion K absorbers closer in. And by the time you go to a large distances, the density of the wind drops significantly. So it doesn't produce any significant absorbers. If not, then density slope must be relatively shallow. But yeah, but at this point from NuSTAR data, we don't see other components. Good point.
Okay, thank you very much, Mr. Keigo. I believe we will be back at 4 o'clock for the session about future missions.